Assalamualaikum and hello to respected lecturers and panel members. We are Team B-4 and it's my pleasure to introduce our team. With me are my teammates Iqbal and Irfan and I am Zulaika Alfia. Today we are excited to present our project titled Design Characteristic of Operational Amplifier. Without further ado, let's begin with the circuit design process. This slide outlines the design process starting from the reference circuit design to the finalized version. The reference circuit utilized 12 transistors, which is 6 PMOS and 6 NMOS, 2 capacitors and 4 voltage sources. In contrast, the finalized circuit design has been optimized to include 7 transistors, which is 4 NMOS and 3 PMOS, 2 capacitors and 3 voltage sources, achieving a simpler and more efficient design. This refinement focuses on reducing complexity while maintaining the functionality, enabling better performance and easier integration in practical application. This slide presents the finalized circuit design created using the Siemens design tool. The circuit consists of 7 transistors, including 3 PMOS and 4 NMOS, alongside 2 capacitors and 3 voltage sources, specifically VDD_N here. It has 3 inputs and 1 output, which is Vout. The circuit is carefully designed to achieve a stable operation using the Siemens tool and precise modeling and validation. This ensures the circuit operates efficiently and meets the design requirement. For this slide focuses on the DC characteristics of the circuit and its biasing requirements. The circuit employs a current mirror configuration for biasing, ensuring stable operation. The transistors are designed to operate in the saturation region, allowing them to function as amplifiers with a linear input-output voltage relationship. The input signals and reference current are configured to ensure the required VGS for each transistors, keeping them in saturation. Additionally, the supply voltage is optimized to satisfy the condition, ensuring proper biasing and enabling efficient amplification.
We're starting on DC sweep. Based on this waveform, it shows the DC sweep results of our circuit design, where the y-axis is the output voltage and the input voltage is at the x-axis. We have made an observation on this waveform where the linear region, it shows that as the input voltage increase, output voltage increase linearly, which reflects the gain of the circuit. This proves that the amplifier is working properly as designed. And at the saturation region, at higher input voltage, the output voltage reached a maximum value which is close to the supply voltage VDD. The output cannot increase any further than the supply voltage VDD. At the very low input voltage, the output voltage show the value is near cutoff region. This is the IV characteristic from our design, which shows the IDS versus VDS, where at the y-axis represents the IDS and the x-axis represents the VDS. The waveform shows that the higher the VDS, the more it shows the transistor entered the saturation region. The IDS starts to increase, not the same VDS. And this is the IV characteristic of IDS versus VDS, where the y-axis represents the IDS and the x-axis represents the VGS. The waveform shows from the initial, the IDS increases, then start to accelerate as the transistor moves from the cutoff to saturation. We make a comparison with the expected output and our own outputs. Based on this IDS versus VDS, from the left, it is the expected output, and at the right is our design output. Our graph shows that our output has more additional curves than the expected output, showing our IDS have wider range for VGS values. And this is the IDS versus VDS. It's very clear that our design output is also have more curves than the expected output. The IDS increasing linearly as VGS increases. Multiple curves for different VDS are shown in our output.
AC characteristic consists of transient analysis. Transient analysis figure shows two waveforms that represent V in and V out respectively. So for the upper part is the V in graph, and for the bottom is the V out graph. For both waveform shows the peak to peak voltage, and we use this formula gain dB 20 log 10 V out over V in to calculate the open loop gain. And then when we obtain the open loop gain, we will calculate the voltage gain using the open loop gain. So for the open loop gain for our circuit is 29.8 dB. Okay, for the next AC characteristic is gain margin and phase margin. Okay, for gain margin and phase margin, we have to find the phase margin first. After we detect the zero, and we draw the line until the gain crossover, and then we pull down the line until the phase margin graph, and then we obtain the phase margin that is negative 251 degree, and then we subtract it with negative 180 degree to get the phase margin. And then for the gain margin, we put the line at the phase margin graph, and then we pull until the gain margin to obtain the gain margin that is 10.712 dB. And then for the open loop gain, we obtain from the transient analysis of voltage gain. We calculated, we got 30.867 volt. For the unity gain frequency, we obtain from the phase margin graph. From the negative 180 degree, we draw the line until phase margin, and then we obtain it by looking at the frequency part. And then for the bandwidth, we obtain from the phase margin, that is 29.79 dB until the saturation part, and then we look at the frequency at the bottom of the graph. So it shows that our system have gain, or the amplifier will amplify. By referring to this graph, the dB gain is about 29.79 dB. That is same with the transient analysis for the signal amplification. After we do the analysis for gain margin and phase margin, we got that the phase margin is in negative value, and then the gain margin is in the positive value, so that our system is in the conditionally stable, or we can call that marginally stable. Okay, for the conclusion, the circuit design successfully achieved linear input output voltage relationship by ensuring all transistors operated in the saturation region, facilitating optimal amplification capabilities. DC sweep result demonstrated expected transition, including linear saturation and cutoff regions, confirming the circuit's gain and operational efficiency. Transient analysis revealed a voltage gain of approximately 29.8 dB, consistent across different validation methods, ensuring a signal amplification that is strong signal amplification. The system was identified as conditionally stable or marginally stable, with a positive gain margin and negative phase margin. The project demonstrates a comprehensive understanding of circuit design and analysis, fulfilling the objectives and showcasing the ability to produce reliable and stable uh, circuit under various conditions. Thank you. That's all from us.